Hello good people, I'm going to talk about alkanes. I'm going to look into rules for naming them and also how we represent them. A number of new terms and concepts are coming your way, so pull up your socks and bring a packed lunch. To begin with, alkanes are aliphatic hydrocarbons. Their names consist of two parts. There is the prefix that gives the number of carbon atoms in the longest continuous chain, and then there is the suffix -ane. The molecular formula for alkanes is CnH2n plus 2. What does all of this mean? Let me bring in a table and then I'm going to explore it. Alright, here is my table. Let me scroll down a bit. If my hydrocarbon happens to have only one carbon atom, then the prefix is going to be meth, and the name of the compound will be methane. The molecular formula for methane is CH4. This follows the general formula for alkanes. I have one carbon, therefore 2 times 1 is 2, plus 2 is 4. Molecular formulas are fine, but they do not tell me much about the connectivity. This is where I need the structural formula. And so if I was to draw the structural formula for methane, I would have the carbon in the middle, and then because carbon needs 4 bonds, I would draw those in, and those bonds are going to hydrogens, because I'm talking about a hydrocarbon. Just like that, we have our simplest alkane. What if I have 2 carbons? Well then, the prefix is eth, and the name of the compound will be ethane. The molecular formula is now C2H, and now I'm going to use the general formula. I will have 2 times 2, that is 4, plus 2 is 6. So the molecular formula for ethane is C2H6. What about its structural formula? I have 2 carbons that are linked together, and then each carbon needs to have 4 bonds. So I'm going to draw them in. I'm going to draw in the remaining hydrogens. If the longest continuous chain has 3 carbons, then the prefix is prop, and the name of the compound becomes propane. The molecular formula is C3H8. Why 8? Well, 2 multiplied by 3 is 6, plus 2 is 8. The structural formula will have 3 carbons in a row, and then because each carbon needs to have 4 bonds, I'm going to draw them in, and as before, I will also draw in the remaining hydrogens. Let me scroll down a little bit further so that I can talk about other hydrocarbons as well. If the longest continuous chain contains 4 carbons, well, then the prefix is but, and the name of the compound becomes butane. The molecular formula will be C4H10. The structural formula will have 4 carbons in a row, and each carbon will have 4 bonds. And once more, I'm also going to draw in the remaining hydrogens. Moving on. If the longest continuous chain contains 5 carbons, the prefix is pent, and the name of the compound will be pentane. The molecular formula will be C5H12, and the structural formula will now have 5 carbons in a row, and each carbon needs to have 4 bonds, and each one of these bonds connects to a hydrogen. Let's keep going. If the longest continuous chain contains 6 carbons, then the prefix is hex, and the name of the compound is hexane. The molecular formula will be C6H14. This means that now I will have 6 carbons in a row that are linked together, and each carbon needs to have 4 bonds, so I'm going to draw those in as well. As before, these bonds will connect to hydrogens. If you have been copying along, and I'm certain that you have, you may have noticed that drawing these structural formulas is a little bit tedious. Luckily, there are a few shortcuts that we can take. Let me scroll back up. And now I'm going to extend this table. which means I need to slide a bit to the right. Aside from a structural formula, we could also write a condensed structural formula and a skeletal formula. When it comes to methane, the condensed structural formula is the same as the molecular formula, and we do not even have a skeletal formula. What about ethane? Well, now we can write a condensed structural formula. And the way we do this is by dividing the structural formula into carbon groups. So I could say that I have CH3 and then another CH3. Time to introduce some new terms. This CH3 is also known as a methyl group. Please note the difference. Methane is CH4, whereas if I'm talking about a methyl group, I'm talking about CH3 that is attached to something else. In this case, I could say that this right CH3 group is attached to another CH3 group, or I have two methyl groups attached to each other. What about a skeletal formula? Usually we do not write in a skeletal formula for ethane either. If we really wanted to, it would look like a single straight line. What does this line represent? When using skeletal formulas, there are a couple of assumptions that we are making. The first assumption is that at the beginning and end of each line, there is a carbon. The second assumption is that each carbon needs to have 4 bonds. Currently, I have drawn just one bond. This means that this carbon on the left and this carbon on the right are missing 3 bonds. The truth is, they're not missing. We are just choosing not to draw them in. They are still there. So when I draw this line, I'm saying there is a carbon here on the left, and it is bonded to 3 other hydrogens that we are not drawing in. The same is true for the carbon on the right. Let me continue with the other alkanes, and hopefully things will become clearer. Alternatively, you might fall down a pit of madness from which there is no recovery. So let me now look at propane. I'm going to divide the structural formula into carbon groups. So here is the CH3, the methyl group at the beginning, and the CH3, the methyl group at the end. In the middle, I have a CH2 group. So now if I choose to write the condensed structural formula, it would look something like this. CH3, CH2, and then CH3 again. Please note that this CH2 group has its own name as well, and it is known as a methylene group. What is the skeletal formula for propane? Well, it's going to be 2 lines in a zigzag fashion. At the beginning of the line I have a carbon, at this corner I have a carbon, and at the end of the line I have a carbon. The first carbon is attached to 3 hydrogens that I have not drawn in. The second carbon is attached to 2 hydrogens that I have not drawn in. And the last carbon again is attached to 3 hydrogens that I have not drawn in. Recall, each carbon needs to have 4 bonds. The bonds that I do not draw in are assumed to be going to hydrogens. Alright, let me look at the next 3 alkanes. So once again, I'm going to scroll down a bit. In case of butane, I have a methyl group at the beginning and a methyl group at the end. And there are 2 methylene groups in the middle. So now if I write the condensed structural formula, it will be CH3, then CH2, CH2 again, and a CH3. When it comes to the skeletal formula, I'm going to extend my zigzag line. I have 1, 2, 3, 4 carbons, and we are not drawing in the hydrogens that are attached to those carbons. Let me quickly divide the structural formula of pentane into its carbon groups. And based on these groups, I can write out the condensed structural formula for pentane. And if I want to write the skeletal formula, I'm simply going to extend the zigzag line. I have 1, 2, 3, 4, 5 carbons. Let me quickly deal with hexane. Note, we have a methyl group, then 1, 2, 3, 4 methylene groups, and then a methyl group at the end. And if I draw a skeletal formula, I'm just extending the zigzag line. If you have been copying along, and once again, I'm sure that you have, you may have noticed that writing out these methylene groups, the CH2 groups, gets a little bit tedious as well. Well, we have a shortcut for a shortcut. And so in case of hexane, I could write CH3, the methyl group at the beginning, and then CH2, but I happen to have 4 of those, so I place the CH2 into bracket, followed by a 4 in subscript, and finally I write in the methyl group at the end. Now that you have a bit of a method, I'm going to invite you to do the next few alkanes. I'm going to give you the prefixes for 7, 8, 9 and 10 carbons. It is hept for 7, oct for 8, non for 9 and dec for 10. Based on these prefixes, I invite you to pause the video, write out the names of these compounds, then the molecular formulas, then the structural formulas, then the condensed structural formulas, and finally the skeletal formulas. I'll give you a few seconds. So the names are heptane, octane, nonane, and decane. What about their molecular formulas? Well, here they are. Remember, they follow the general pattern of CN, H2N plus 2. So for example, in case of decane, N is 10, which means I have 10 carbons, and then 2 times 10 is 20, plus 22, 22 hydrogens. I invite you to write out the structural formulas. Yes, that means writing out all of the carbons and all of the happy little hydrogens. Are we having fun yet? Let me slide to the right and invite you to write out the condensed and skeletal formulas as well. And here we go. Here are the super condensed structural formulas. So for example, for decane, we have a methyl group at the beginning, a methyl group at the end, and in between we have 8 methylene groups. The last thing we need to do is draw the skeletal formulas. Once we have a longer chain, the trick is to know when to stop drawing the zigzag line. Let me do heptane first. 1 carbon, 2, 3, 4, 5, 6, 7. In case of octane, I have 1, 2, 3, 4, 5, 6, 7, 8. For nonane, I need 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And for decane, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Generally speaking, in organic chemistry, we prefer the skeletal formulas. They are quick to draw, and once the molecules become even more complicated, they make it easier to see what is going on in terms of the molecular structure. I can hear a number of you questioning my heritage. So let me wrap this already long video by quickly mentioning the main points. In terms of language, you need to become comfortable with the prefixes for the first 10 carbons. When it comes to alkanes, the suffix will be ane, and so we will end up with names like methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. A CH3 group is known as a methyl group. A CH2 group is known as a methylene group. When we draw skeletal formulas, each beginning and corner, or if you like, each zig and each zag, represents a carbon. Although we do not draw in the hydrogens, they are definitely there. That is all for now, and I will see you on the flip side.